Among all the feasible interconnection topologies for computing systems, multi-stage interconnection networks have become very popular because they are able to provide a high network throughput with low latencies, as well as to meet the needs of new applications and the demand of new services. In high-performance interconnect for clusters, the communication model assumes a lossless network, so packets cannot be dropped to deal with congestion, as happens in other interconnection environments. Therefore, mechanisms for congestion management are needed to palliate the problem of congestion in these environments. Congestion problem appears when an output link becomes overloaded because several flows are sharing that link and packets start to accumulate at the buffers. It will not be a problem if all flows have to cross the same output link. The problem shows up when packets cannot advance although the requested channel is idle. In this situation, we can classify flows into two groups, the responsible and the non-responsible flows. Next pictures show the process of creating a congestion tree. In this figure, an initial situation for three different flows crossing the switch is shown. Let us assume that the overall input traffic rate for X plus Y flows is greater than the bandwidth of the output channel. In this situation, packets belonging to both flows will have to compete for the output channel, and as a result of that, the output buffers will start to accumulate packets. If this situation remains for long, these pictures show how congestion is spread along the previous switches, stopping and accumulating packets. This situation provokes a new congested output channel at the previous switch. As it can be seen, the congestion having spread along the congestion tree toward its leaves, affecting several switches. Congestion management has been widely studied over the years. Although some mechanism has been proposed to solve the congestion, they do not guarantee that corrective actions are only carried out on flow responsible for congestion. So the challenge is to develop effective and efficient mechanisms which apply corrective action only over the flows truly responsible for congestion. The new proposal is called Marking and Validation Congestion Management and consists of an end-to-end mechanism based on the use of explicit congestion notification. This new mechanism is not proposed for any standard interconnects in particular. The new proposal uses buffer thresholds at both input and output channels to detect a possible congestion situation. This mechanism proposes a new packet marking strategy to detect congestion that combines packet marking at input and validated at output buffers. The advantage of applying this new strategy consists of classifying the network flows in three types: hot, cold, and warm flows. As a consequence of the flow classification, the new mechanism proposes two levels of corrective actions at the origin host. The first level is based on adjusting the packet injection rate by using a dynamic window, and the second level will reduce even more the injection rate by introducing a waiting interval between the injection of two consecutive packets. In order to analyze the impact of the more efficient packet marking strategy applied by the new proposal, the mechanism has been evaluated under different network configuration, traffic load, and congestion degree. As it can be seen, the new mechanism achieves better performance if it is compared to the previous proposals. To conclude, a new mechanism, referred as Marking and Validation Congestion Management, based on the explicit congestion notification technique, has been proposed. The new mechanism contributes to a new packet marking strategy and the first set of corrective action. Finally, as a result of the deeply performance analysis done, the new proposal is able to effectively manage congestion regardless of the network configuration, traffic load, and congestion degree.